Hello everyone. Today we are going to present our work on tutorial 5 of our course subject Mechanism Sessional for autumn semester 2025. We are going with the topic of windscreen wiper. Myself Tushar Ranjan Verma, role 23ME30069. Let me introduce you to my group members. Khem Kumar Varsagade, Supam Kumar, Siddharth Jain and myself. Now let's look at the table of content. So let's start with the problem statement. We were given the problem to synthesize and make a simulator for the windscreen wiper mechanism shown in tutorial sheet 2 question 6 along with no quick return effect, and in the simulation we have to mark the wiped area and add any new area which we might have. So this was the question in tutorial 2 question 6. uh, we can see a wiper mechanism and we have the dimensions and angles given for the same. Now let's look at the objective of our project. Our very first objective is to synthesize a 4-bar linkage which will do an oscillatory motions that will be suitable for our windshield wiper. Then we have to simulate the mechanism and visualize the wiped area on the windshield. And later on we have to compare theoretical expectations with simulation outcomes and understand practical design considerations too. So let's start with the theory behind our mechanism. At first, let's talk about the Grashof criterion. This criterion determines the range of motion. That is, like if any, at least one link in the whole mechanism can at least perform the complete 360-degree rotation. For the mechanism shown, we will have like 4-bar mechanism. We have 4 bars, out of which the smallest one will have the length of S and the largest one will have the length L. The other two bars have the lengths P and Q respectively. If the total addition of lengths of smallest and largest length is less than or equal to the other two link lengths sum, then the Grashof criterion is satisfied and we will have at least one link that can perform a complete 360-degree rotation. Then we have the degree of freedom calculation. Number of links is 6, number of joints is 7, and connectivity is also 7 as all the joints are revolute joints, and we get our degree of freedom of this mechanism as 1. Now let's talk about the quick return ratio. As the name suggests, it is a ratio of time of forward stroke upon the time of return stroke. And for our mechanism, as it is said in the question itself that it is not required in this mechanism, so we have to keep it to 1. Like our quick return ratio for this mechanism is equal to 1. For keeping it to 1, we have changed the dimensions of some links like which we are shown here. You can see.
Hello everyone, my name is Khem Kumar Barsagade. My roll number is 23ME30002. Now I'll be explaining to you about the working of a simulation. Here we see the synthesis and the simulation of our mechanism. What we have done here is that we have kept the crank and the coupler lengths as same and then changed the dimensions of the other links so that we get the no quick return effect. Here we can see that the dead center configurations are at 180 degrees to each other. This ensures that we get a quick return ratio of 1. That is, we have a no quick return effect. Here we have made our mechanism in SolidWorks so that we get a 3D view of it.
Hello everyone, my name is Siddharth Jain. My roll number is 23ME30060 and I will be explaining the MATLAB code for you in this simulation. So here these parameter values we have received from the linkage which my friend showed you earlier, and these here we are defining all the links which will be required in the mechanism. Here we are defining all the simulation parameter. Here we are generating the arrays which will store the values of the path coordinates, and here we are writing the parameters for the figure generation. Here we are defining the ground plate, and here we are defining all of the other joints. Now this is the simulation loop. This is going to run once for each rotation of the crank, and at each rotation we are going to first update everything, unpack and update everything. We are going to store it in the arrays, and we are going to update the parts and find the fixed sweep region. And this is the function which we are calling as part of the main. and these parameters we are giving it to the function. So let us now see how the simulation runs. So this is how the simulation is running. Here, this crank rotation is causing this dotted line is because it is a 3-member rigid body, and all of these other links are 2 members. As you can see, this rotating of the crank is causing this area to start getting shaded and widened. Okay.
Shivam Kumar, the roll number 23ME30059. I will be dealing with the problems faced while doing the project. There were link length constraints. As you can see that some combinations of link length were violating the Grashof conditions, which will prevent so that the rotation of the crank would be leading to the full extent. There were numerical changes in the link ratios, which resulted in the no possibility of no quick return effect condition. So we have to scale it to 1. Acting dynamics. We ignored the possibilities of different types of inertia and friction variation so that the real torque demands would have been a little bit higher. The solutions to that problems which we face were we make sure that the two dead centers are at 180 degrees so that the crank and coupler dimensions were same and fixed them at the same dead center configuration. This gave us an idea about the location of the second pivot in the ground frame. We then choose it at a sufficient distance so that the Grashof criteria is satisfied. As soon the Grashof criteria is satisfied, there was a complete rotation of the coupler. There were different torque requirements for the motor. The motor to be used for the driver link should provide sufficient torque to move the entire mechanism along the wiper. A relatively lightweight material so that the wiper arms and joints would have to ability to reduce the force and the length and the torque would be have a very less value. The wiper should be relatively smooth so that the friction force would be very less, so that the torque would be requirement would be very less. The friction between the joints and the lengths of the mechanism will also consume some of the motor torque, so that the lubricating oil or lubrication would help in the practice would be making the smoother flow. The different types of wiper designs would have also been seen as a tandem design, when with the wipers move in the same direction with maximum overlapping coverage. Opposed system, when the two blades move from sides toward the center. Single arm wiper, one blade sweeps across the windshield in a single arc from a central pivot. Single arm controlled wiper, a more advanced system where the wiper arm extends and retraces as it sweeps, covering a larger area. Driver position, wiper pattern is optimized to keep the driver's speed only for the clear view. Now we're seeing out the ideas.
So now on to our next section. The first point here explains us how we are calculating the wiping speed of the wiper. So the logic behind it is that one whole rotation of the crank would give us one wiping cycle of the wiper. That is, it would go from one extreme position to another and then back to the first one. So for a motor RPM of n, that is n rotations in a minute, would give us n wiping cycles in a minute. Then our second point explains us how we could increase the area wiped. So by increasing the length of the link on which the wiper is attached, we can increase the area wiped. It is because the increased length would increase the arc length on which the wiper moves.
Now let me show you future improvements which we can add to this simulation. So right now what we have done is we have hard-coded all the parameters into the code. For future purposes, what we can do is make it so that each parameter's value can be changed at runtime rather than right now as hard-coded values, so that we can dynamically we can check how each parameter varying causes a change in the swiped area or the velocities or change in speed or the torque on the motors. So another way future improvements can be made is optimizing it or using maths and some complex algorithms to maximize these wiping area while minimizing the torque. Because there is going to be one value where there is going to be one value of torque and for each parameter where the wiping area is maximized but the torque on the motor is minimized. We desire here to minimize the torque on the motor because a higher torque motor will consume more power from the engine. And the best improvement which is possible is to create a physical prototype, because there we can create real world variations, and there are also unidealities which are present in the real world which cannot be accounted for in the simulation, such as accounting for friction, accounting for tolerances, extra gravity. So in conclusion, we have synthesized the wiper mechanism which was required in our project's objective, and we have completed all of which was asked for us. We provide the mechanism created by us provided a uniform wiping motion. The swept area is a realistic representation, and it outputs meaningful kinematic data so that design can be evaluated. Moreover, the simulation framework easily allows design parameters and could serve as a base for advanced windshield wiper optimization. So varying variable speed or including multiple arms or improving linkage geometry could be done in the simulation as well. Thank you for your time.